Yeah.
Good.
It starts being recorded.
Okay.
Okay, so it's good to have everybody going back to this remote conference room again. And this time we're very happy to have Klaus Mosegaard here presenting his work on the Monte Carlo Methods and the geophysics inverse problems. Klaus Mosegaard is a professor of computational geoscience at the University of Copenhagen. He has a background in mathematics, physics, and geophysics with doctorate degrees from the geophysics and physics department in Copenhagen, and postdoctoral study in Albert Harentola in Paris. His main scientific contributions are on probabilistic inverse problems with special emphasis on Monte Carlo techniques for highly nonlinear problems. He has contributed to a wide range of studies in Earth and planetary physics, including analysis of lunar interior and recently mapping of the crustal structure of Mars based on data from NASA's Mars Insight project. Okay, let's leave the time to Klaus and welcome Klaus for his nice talk.
Thank you very much. I began my career as a PhD student with studying the methodology, the Monte Carlo methodologies, and especially using some physics, thermodynamics insight. It was very interesting, and then I went on doing that for a while, and then I started applying it to all kinds of things and helping people out with solving their problems. I did for quite some years, and then as my hair grew gray, I started going back to the interest from my youth, and now again I started looking into the inner workings of the Monte Carlo's methodologies, and that is a great pleasure actually, because of the developments.
Could you click the got it somewhere?
That's it.
I did not.
Okay. Maybe I can just press the.
Yeah.
Because otherwise it doesn't record.
And we try.
I cannot operate. Maybe you can. It doesn't. Maybe you can do it.
You need to consent it. I think you can just. Okay.
Okay.
This is awkward. Okay, I see.
Oh, you want one.
That.
There we are. It
Okay.
works, I think.
Okay.
Great. A little bit of technology challenges. Okay. Monte Carlo methods as a tool for solving inverse problems or optimization problems has developed a lot over the years, and it's used a lot. I remember when I started this several years ago, my postdoc advisor, Albert Harentola, he was a great believer in the use of Monte Carlo methods, and even I, who liked them, said that can you imagine that those methods will be of any big use, because it's a very time-consuming kind of calculation. Can you believe that that will be used by anybody? And he said, he was very courageous and said, everybody will use this in 20 years from now. I said, okay, then let's go on working with it. And I don't think everybody's using it, but I think it's amazing how widely used it is actually. And of course, it's helped a lot by the improvements in computer technology. But it's also there are also a lot of good ideas around in improvements of these methods. But I believe that, but there's also a category of certain researchers that are very skeptical about it and actually are resisting a lot, and believe that it's fundamentally difficult to use Monte Carlo methods when you have more than 20 unknowns or 20 parameters you want to estimate. And there's a grain of truth in that actually, and I think that's one of the starting points of my research at the moment is to acknowledge this difficulty. There's a fundamental truth in this in the slowness of Monte Carlo methods. So the purpose of my talk is to discuss this problem, and then hopefully I can try to convince you that there's at least one way of maybe making Monte Carlo methods useful even for large-scale problems. And when I say large-scale problems, I mean problems where you have a lot of unknowns. So I will first tell you a little bit about why we do Monte Carlo, just a very basic stuff in the beginning, just to show how it works, and then I will talk a bit about the difficulties of why Monte Carlo often gets stuck when you try to use it on large-scale problems, and then finally I will try to convince you that there may be a way of getting around that and actually solve very big problems with Monte Carlo. So that's you have probably heard about the so-called curse of dimensionality, where you try to search for a solution in a high-dimensional parameter space, and then because of the size of the dimension, you just can't do it because all directions are wrong, so to speak. And that, so it seems kind of like a very optimistic goal to have to make this work in high dimensions. But let's see if I can convince. I hope I can convince you at least, and you feel free to express your disbeliefs or beliefs in any way you want.
Already?
Yeah, why not? That would be fine. Let me have a few initial words first. I think if you are very skeptic, you will be very happy in the beginning because you see some horrible examples of the collapse of the Monte Carlo methodology. Let's see. So now I just have to probably.
Left.
Oh, okay, good. So let's first just show for those of you who may not have any clue about what we're talking about, let me just show you how you can use Monte Carlo to solve inverse problems using some kind of a probabilistic view of this. So here's a simple drawing showing a two-dimensional space where you have a probability distribution in that space, and the probability distribution we have here, imagine that this is the result of, this is the output of a probabilistic analysis of an inverse problem. So the space you have here is a parameter space. So in this case, you have two parameters, and the distribution gives you the likelihood of each probability of these parameters, and then you have high values here. So I imagine it's a little bit complicated problem with two bumps, two peaks on the probability. So you have essentially two good solutions, and if there's some uncertainty that is described by the probability density. And if this had been a simple, let's say, Gaussian probability with one bump and a simple structure, then you could have communicated the result by just giving people the mean and some covariance, some variance, some spread covariance matrix, and that would have been a complete description of the distribution. But in this case, you can see it's very non-Gaussian, so you can't do that. I mean, for instance, the mean would be somewhere here, which is a very improbable answer. So you would have to do something else. And the idea behind the Monte Carlo is quite simple. It is to say, okay, if we have time enough, why don't we just produce samples from this probability density, which means points with a density equal to the probability density. And then from these sample points, we can then, first of all, illustrate somehow, at least in 2D we can do it, or maybe 3D, illustrate the density, because it's simply giving us the, I mean, I think you even have, you can see here, you don't know, in reality, you don't have a picture of the distribution you are mapping, but you have, if you can produce samples, then you almost have a picture. You can even, because the density of the points is the same, And from there, you can calculate all kinds of, you can calculate mean values, you can calculate variances, you can calculate all kinds of integrals of the distribution. And this is the basic idea of Monte Carlo, to be able to do that. But of course, it is easier said than done, because how do you generate these points? So that's what I will talk about. Let me just show you, just to jump from this very what shall I say, abstract view of things to what it would look like on your screen if you actually solve an inverse problem in this way. Let's imagine a seismic problem where we have seismic data. Let's say some stable seismic reflection data, and we want to produce sample models from that. Then it would probably look like this. You have the seismic data. These are traditional oil and gas, groundwater, if you prefer that, the seismic data, and you want to find acoustic impedance models that explain this data within the error bars of the data. And if you ask a Monte Carlo algorithm to do that, it would produce these sample points in the parameter space, and each point would be a model of the impedance of the subsurface. And what you see here is a movie where you jump from point to point, from sample point to sample point, so you can see little changes for each jump. But each new model is a new sample point in the model space, and the points here, they are chosen so the density of points is equal to the density of the distribution that we want. That's, by the way, called the posterior probability distribution, which is a term from the Bayesian statistics, and it is the distribution that gives us the possible models and the uncertainty of these models. So if you look at this model here and you see some changes, the changes, they illustrate the uncertainties. It's just a movie of allowed models of solutions that are allowed within the error bars of the data. So the whole idea is actually very simple in some sense. If you can make it work, and that's the story about this. If you can make it work, because how do I know that this is not just some movie of something that has nothing to do with anything? I mean, I have to make sure that I can actually do this sampling. This is the difficulty.
What do the blue and green colors mean?
It's just the acoustic impedance. So you have low impedances for the blue and high impedance for the green. I could have put a scale here. It's actually would open a Pandora's box of difficulties in the discussion of that. So I just don't want to do that. But it's of course a valid point. Okay, so let's just so we ask the question, that's the theme of this: how difficult is it to obtain such a sample? In 2D, it's not that difficult to do, but the model we just saw with this movie, it would be a very high dimensional thing. So, okay, so let's talk about Monte Carlo algorithms in space of very high dimension. Let's try to see what happens when we have this toy problem like this with 2D, and then try to upscale it to many dimensions, and let's see what happens to the sampling time. And that can be done analytically, actually, to some extent, if at least under simplifying. I can show you an analytical example which illustrates this. And for those of you who think or who dislike Monte Carlo methods, are very skeptical about its application, you'll be very happy to see that it really breaks completely down. Let's take a look. So now I will just look at something that should be very simple, right? Let me look at a probability distribution that is Gaussian. There's some mean x0 in the space I want to sample, and some covariance matrix C. You can imagine you have it here. So here you have the space. It's actually just a 2D space because it's very hard to plot 80D space, of course. So I have a 2D space here with a Gaussian, and now I'm going to to sample this, and what I do is I and that is the most widely used Monte Carlo methods. They are random walks, so they make jumps in the parameter space, and the jumps have to be described, of course, and we describe it through what is called a proposal distribution. The proposal distribution is the distribution of steps that we take. So if we are at a certain point in the parameter space, then what is the probability that my next step will lead to a certain point? And that's given by the proposal distribution. And because it is proposing a new state, a new point. And I assume here that that is also Gaussian. And it is actually just a very simple one. It's an isotropic Gaussian. So it's just the same in all directions. So at every step, I make a move according to this Gaussian. Send the Gaussian centered at the current point, and then I perform a move. And then when I go to the new point, then the Gaussian will move with me, and it will propose. I can use it to propose the next step. And then there are some rules that we use to take the step. And we are assuming here that we are running the good old so-called metropolis algorithm, which is an algorithm that will reject any step that leads to a lower probability on the target distribution here. But if we have it will accept any move leading to a higher probability. But if the proposal here suggests that we should go to a lower probability, then it will accept it with a certain probability, which will be equal to the ratio of the proposed and the current point probabilities. So that is the metropolis algorithm. Okay, so let's try and run that one on this problem, and now I will play a little game where I try to step up. I first use it in 2D, which is actually the one that is illustrated here. You have a 2D distribution I want to sample, and then I can compute. I will assume, to make it life easy for this algorithm, I will assume that it actually starts at the highest probability points. So it's not, I don't want it to find the peak probability. I just start there. I give it I'm very friendly and tells it where the best probable point is. And then I can actually compute analytically what the probability, I can compute what the probability is of accepting the next step in the process. So I'm standing at the peak. I take a step away from the peak, and then I just compute what the expected acceptance probability is for that. Actually, all points are worse than the points I'm starting in. I'm starting in the best ones. They're all worse. So the closer the point is that is proposed, the higher chance is the chance that it will be accepted. If something far away with a very low probability is proposed, it will probably not be accepted. But I compute the acceptance probability mean, and it gives you a probability of 0.4082, which means that I roughly have to wait for 2.5 iterations to have an accepted point, accepted move. And that is very nice, because it's not a big problem. I just run the algorithm and will produce a lot of accepted samples. So I will move around. Okay, now I will say one thing I forgot to say. It's very, I said it halfway. My proposal distribution, the one that should suggest new points, is given by a Gaussian that is isotropic, and it has a variance of 1. It's just something I assume. But the target distribution has a covariance matrix like this. Let me just show you the previous project. You can see it's elongated in one direction here. And in 2D, it's not a big deal, but in high dimensions, we have to specify how wide it is in all directions. And what I assume here is that the variance, and that's given by the variances in the different directions. And what I assume here is that the variance in the first, the variance in the first dimension is 1, the variance in the second dimension is 1/2, and then so on. So it's actually it has a covariance matrix where the diagonal that has 0 off diagonal elements, and it is dropping as 1/n for as a function of the dimension. So I think it's 1/, I mean, that's the 1/, what is it called? 1/f noise, I think that's given by that. So by that model, if you like, that kind of statistics. Okay, so this means that the probability distributions I look at in high dimensions, they have different variance in all dimensions. They are narrow in a high dimensional sense. They in a high dimensional sense, they are narrow. So that's how my experiment is set up. In 2D, I get this waiting time between accepted models in 10 dimensions, which is something that is quite common in applications, maybe 10, 20. My waiting time expected will be 6,318 iterations, which actually is a lot already. And in 100 dimensions, the waiting time will be 10 to the power 80. That means forever. I mean, you will never have anything accepted. You're completely out of business in 100 dimensions. And the reason is, of course, that my step length, my proposal distribution that suggests how far I should go will be only hitting something with high probability in certain few directions, but in most other directions, it will step out of the high probability. So it is this one is kind of having the same width in all directions, but when you use that to walk around, then in most directions it will step out of this distribution. I can of course try to make this more narrow, then I will do a better job. But then on the other hand, the steps will end up being too small, so it will take a long time to move around in the directions where it's wide. So there's no way around this problem. And of course, people's Monte Carlo sampling problems are usually more complicated, but this is the essence of the difficulties you are running into, that there is a mismatch between this guy here, the step proposal thing, and the distribution you are trying to sample. There's a complete mismatch. And to avoid a mismatch, you have to know something about the problem. So there's something here. This is an example of a blind algorithm. The algorithm is blind in the sense that this guy here doesn't know anything about the structure of this one. If you imagine that you could design this so it has some built-in knowledge of this, I mean, what would be an extreme case of that? That would be that this one is equal to this. That would be good, because then it would propose good things all the time, and you would have a fantastic convergence. So, but that would amount to having the solution already. So I mean, that would be meaningless. Then you would not even consider running this thing. So this is the dilemma, I think. Okay, let's just step a little bit aside and try to take a look at what is the structure of a real problem, just to see what we can do. Sometimes, for instance, in machine learning books, you can see that it is suggested that solutions to problems, optimization, sampling problems, that they are very often located in a lower dimensional manifold, so that actually the spatial setting is more or less empty in some sense, but the real good solutions are found along a manifold, and if you could find that manifold, then you could just sample inside that one, and then everything would be much easier. And that is certainly sometimes the case. And especially if you can find a local coordinate system in that manifold. I mean, it doesn't help you very much to know that the points you want to send should lie in a manifold if you don't know where it is, so to speak. So if you could find a local coordinate system in that manifold, then you could effectively reduce the dimension of the problem. So in that way, you would not really have changed and made the Monte Carlo method better, but you would at least have modified your problem so you can more easily do the sampling. That would be great. And this is this claim, I think, is correct. But I think there's also a pitfall in this claim here, because it's not as easy as it looks. And I've just illustrated with a little cartoon what the problem is. So here what I would like to look at here is the dimensionality and degrees of freedom of the inverse problem. Here we have what I would call an easy problem, and this illustrates that you have a high dimensional space, and then you have a probability density inside that one, which I would call a space filling. Just my own word, space filling probability density. It's a density that is not located on a narrowly located around a manifold, but it's something that is actually gives you a significant probability everywhere. We have n degrees of freedom, so it's probably high in many parameters, and this problem is easy to deal with, because, okay, it may take some time to have enough points to represent it, but you are not, when you suggest a new point, every time you suggest a new point, it has a good chance of being accepted, because the probability is not zero. I mean, you go in some direction, and the probability is not just zero in this direction. It's space filling, so it's not a difficult distribution to sample. Here we have the thing that is often mentioned in books on machine learning. Here you have a probability distribution that is restricted to a manifold. So here's an easy one. What do I mean by easy? I mean that we have a narrow distribution, but it is actually parametric. You have a description of where it is. You have a local coordinate system, in this particular example, it has 1 degree of freedom, and the surrounding space is 2D. This is a simple example. It's very easy to sample if you imagine that this is a distribution, that is a density that is non-zero around this manifold. It's very easy to sample because you have it's parameterized, so you always know which way to go. So you can just sample it as if it was just a 1D distribution. So that is easy. But imagine that you have this example where you also have a 1 degree distribution, 1 degree, you have a one-dimensional one-dimensional subspace or manifold where the distribution is not zero and you are still embedded in a 2D space. But in this case, it's a non-parametric distribution. It is you don't have a coordinate system. It could, for instance, be a fractal, in which case it may not even just have 1 dimension, but maybe 1.4 dimensions. It could be a fractal structure. There's no way, when you're standing in one point, there's no way that you can easily find out which neighboring points are also in the distribution. In that case, it is hard to sample this one. It did not help you to reduce the dimension. You would still have to look around in the 2D space in order to find other points, nearby points that have a high probability. So my point here is that it's not enough. I mean, dimensionality distribution is not enough. You can still have a problem that is just as difficult as the original one. And you can go up to high dimensions. It doesn't help. I mean, in this case, this one is still easy. You may have let's say a one-dimensional structure here, and it's very easy because it's parameterized. But here, because it is embedded in high-dimensional space, and you don't have a local coordinate system, you don't know where to go in order to get the next high-dimensional point. And it gets worse and worse the higher this embedding spaces. So the dimension of the embedding space is important still. So it's not enough to reduce the dimension of the space. You also need a local coordinate system or a parameterization of this. And yeah, okay, what does this have to do with any realistic case? Let me just go back to the seismic example I showed you before. Here we have the seismic data. This time, I'm going to impose a constraint on the models, and the constraint is that it should be a realization from, I don't know how much you know about geostatistics, but there's something called multiple point geostatistics, where you have a training image of possible solutions, possible geological structure, and then you say, okay, let me analyze the statistics of this, and then generate new models that looks the same, but it has the same statistics. It's widely used in modern geostatistics, and you can use that as a constraint on the inversion of the data, because you say any model that has a high probability must be models that have the same statistics as my training image. And you have a method, the multiple point statistical method, that can generate such models. If you have a training image and you have a statistic, you can generate models from that. And you can even do it by local updating of the model, treat it a little bit, and you can find new perturbed subsurface models that has the same statistics as your training image, and then you can try to see if that fits the data, and you can do that in a Monte Carlo. The Monte Carlo strategy, generate new subsurface models according to the statistics and see if it fits the data, and you can use that in a metropolis type of thing. The problem here is that the models here, although it restricts heavily the permitted models. Those models are not lying in a nice space that you can describe by the coordinates. It's actually an irregular, non-parametric, but possibly low-dimensional subspace of the parameter space that we define. And this is the reason why, because I've tried it many times myself, and even have some publications where we do it. But you have to, it requires a lot of electrical power to do this inversion, because you have to sample and sample and sample. It's really a very, very slow process, because this space, it doesn't help you that you have a low dimensional constraint. It's actually still the high dimensional space you are sampling in. So this is the very, I believe this is the reason why this kind of inversions, which I really tried to promote, is very difficult. Okay, I don't want to. I said a lot of things. I don't want to do the confusion thing here. So, okay, I think after this, what I said now, we have learned that the Monte Carlo sampling, you can demonstrate that there are examples where the Monte Carlo sampling is just completely unfeasible in high dimensional spaces, even when you sample simple distributions. And we have also seen that the reason seems to be that the way we take our steps in the parameter space, the so-called proposal distribution, is very unlike the distribution we want to sample, the target distribution. there's a mismatch between the two. And this is characteristic of the what we call the blind algorithms. So what we want to, so what I will propose here is that we try to remove the blindness of the algorithm. We try to build an algorithm that knows something about the distribution we try to sample. But we still have to be think about what the realism here. We want to think about real inverse problems. What do we have? What do we know about the problems we have? What can we expect to know? And here I would like to show you a way to move forward, I think. So here's a simple cartoon showing an inverse problem. So you have some data here, and then you have some possible, this is my drawing of the possible models that could explain the data. So it's supposed to be a piece of geology. I don't know how nice it looks, but that's what it is. And then I have three, in this case, I have apparently three solutions, essentially, that can explain the data. And there are some uncertainty, uncertainty around it, and they all map into the data, and the uncertainty of the data is illustrated by this circle here. And of course, the inversion is essentially to go backwards and find the correct models that fit the data within the error bars of the data. And then what I would propose here is to say, okay, now let's try and see what happens if we introduce, if we replace, not replace, that's not the right word, but if we introduce a physics model of the process, in this case the wave, in this case the wave propagation, that is simplified. So it does not take into account all the complications of real wave propagation, but it's just a simplified model. And I'm sure you know a lot of simplified models of wave propagation. You can have your own favorites here. And let's see what that would do to the solution. So if I now, instead of using the correct connection between model parameters and data, then we try to see what happens if I introduce a rough and approximate connection, and I use that for my inversion. So I take the data, I use some poor physics, some approximate physics, and then I do the inversion. And then of course I will hit the wrong solution. That's not surprising in any way. Maybe you will be happy with that one and go home, that's fine. But let's say that we are more ambitious. We want to do things not just better, but we want to do it just as well as if we had the correct connection between data and model parameters. And so what I will do now is I will introduce what I will call the modelization error. So if I knew how bad this approximate physics is that gave me this wrong solution, then I would have what I would call the modelization error, and hopefully it's a good estimate of the modelization error. So within the modelization error bars around that one, you would find the correct solution. So if it's just a game I play, if I had that modelization error, then I would have defined a subspace where I would probably find the correct solutions. So let's try and see how that could be used. So here I think I should show a picture of a famous physicist who was a co-author of the famous books Landau and Lifshitz. You know, these are the Russian books about physics. The Russians, they didn't have access to the Western literature about, if you go back 80 years or something like that. But Landau and Lifshitz, they wanted to write some books about all of physics, some really basic, strong fundamental books. So what to do when you don't have access to the literature? You just work out the whole thing yourself. That's the way. That's very recommendable strategy if you have time. I don't think it's good for a PhD thesis, but it's a way to do it. So they did that. They just wrote several volumes of books about physics, and they are now really benchmark books. So it's great. But one thing he said was that an important part of the physics is the knowledge of approximation. So it's actually the reverse of machine learning. Machine learning is to say, okay, I have a physical problem I want to solve. Why don't I do it by statistics? So I just take a lot of examples of connections between parameters and data, and then I learn what the connection is, and then I use that to solve an inverse problem. This is the reverse. You say this is the old-fashioned way. We say we can't do that. We don't have statistics now. We want to work out some simplified theory that captures the fundamentals of the process. That's what we will try to do here. So what see, this is kind of the opposite of machine learning. We try to learn a simplified model of physics, and we try to use that in our calculations. Let me show you an example here. So here we have this is a pile of sandstone, if you like sandstone. And as you can see, a lot of tiny layers here. So let's imagine that we have the product of velocity and density all the way down, which we call the acoustic impedance. And let's imagine that you have a plot of the acoustic impedance as a function of depth or layer number. We have 1,000 layers here. So we have 1,000 values of acoustic impedance down through this. So to describe, I mean, this model here, because it has 1,000 parameters, it has 1,000 parameters, so it's a point in a 1,000 dimensional space. And let's try and compute artificially the data of this thing. And here we have it. So this is full waveform near vertical response. So I sent an acoustic wave, in this case, down through this segment and return back as reflections. And I solve the wave equation exactly. So it includes all orders of multiples and stuff. So it's just a full waveform response. This is just 5 copies of the same. Some people who look at reflection seismic, they like to look at these diagrams. So I just put 5 copies. And now I would like to approximate this. I do that in a very well-known way. I use the convolutional model that is very popular in reflection seismic. So I have a wavelet, and I convolve that with the reflectivity series. From the acoustic impedances, I can compute the reflectivity at every little layer boundary, and I can convolve the thing, the wavelets, which is the input impulse from above. And then I get this signal here, which looks very similar to the true signal in the beginning, but with all the echoes they take over, you can see how different the two signals are. So this is my rough physics, my rough approximation to the physics here. It's a very popular approximation, so it's very well known. And here's the error, almost 0 error in the beginning, and you have in the tail you have a quite big error. Okay. So this is an example of a situation with many parameters, true physics and approximate physics. Okay, let me jump back to the idea now. The idea is now that my problem, my full problem with full physics, it is the solution to that, the inverse solution to that, which is a probability density in the model, in the parameter space, the model parameter space. This is called the posterior. Here's the true posterior. It has some structure. I don't know what it is, and it's only drawn in 2D. I have 1,000 dimensions, but it has some structure. Now, if I use the approximate physics, in my case, the convolutional model, and I solve the problem, which I can do it, by the way, very fast, because there are methods you can solve this very fast. Then I get a solution. It should have been this one, but it's only this one. it has some similarities, but it also has some differences, important differences. You can study for yourself what she was the same and what is not the same. So this is the approximate posterior. Now I told you that if I want to run a Monte Carlo algorithm, it should use a proposal distribution, step distribution that is as close as possible to the true distribution. What I will do now is I will use one that is equal to the approximate posterior. So I'll use this one to jump. And when I do that, if I do that, then of course I would, if I do that without anything, it would just give you the wrong result. But it turns out that if I, in my Monte Carlo algorithm, use as an acceptance probability, this is the probability that I actually accept a jump, and it has this form here. This is the, from the 70s, this is the Hastings modification of the metropolis. It's called the metropolis Hastings algorithm. Accepting a step should be done with a probability that is equal to the ratio of the this distribution in the proposed point divided by this value in the current point. But then I should also multiply with the ratio of the proposal probabilities back and forth, so to speak. So, and I know what the proposal is. This is my assumed proposal distribution, so I can compute this one. So what it does is it is proposing in a way that is reasonably close to the true distribution, but still wrong. But the error in the bias is divided out here, because of course if I propose according to this one, we give some kind of, it will have some kind of bias in the proposal because it likes this one. It's supposed to sample this one, but that bias will be divided out of the acceptance probability, and then so the result is an algorithm that actually asymptotically will sample the correct distribution. So this is the idea. So let's try and do that on our problem, but there's a little thing here because I talked about this modelization error. So how do we get that one? So here's the true acoustic impedance. If I take my convolutional model and solve the problem, there are simple and very fast way to do that. Then I get this one here, which is kind of good. At least in the beginning, it's quite good. You can see it looks very nicely there. But when you come down here, when you have big reflection coefficients, that's exactly where the multiples start getting strong. Then I get something that's not so good. But now I do something very simple, just for exercise. I say, I'm going to make a Monte Carlo algorithm that will sample this one and will use this one to help proposing good models. So what I do is something incredibly simple just to see if it works. I make in the parameter space, I define a proposal distribution which is centered at this one. The center point is this model, which is a point in space, and then the spread or the variances are given by the modelization error, which is essentially the difference between the two. So I can take the difference. If I had this true model, if I had this one, you don't have it, but if I had it, I could just subtract them, and then I could estimate what the modelization error is as a function of depth. And then I could use that variance around this one and use that as a proposal. But that's just a dream, right? Because I don't have the modelization error. In real life, you don't know what the true model is. So that's the problem. What to do about that? And this is probably the key trick in this method. What you do is you take, of course it is here, but let me just explain. What you do is you make a little down to earth trick. You say, okay, I don't have the modelization error, but I could play a little game. I could play the game that this one is the true model. And then I could try and solve a problem. I could easily generate the full waveform response from that one. then I could try and make a second order approximation, which would be even worse, using the procedure I just told you, and then could subtract 2. And considering that this model is pretty close to that one, then the modelization error I would get by making a second order approximation would probably be close to the true modelization error. In this case, I can check how close it is. Here it is. Here's the true modelization error. This is depth. This is error. Here's the true modelization error. And here's the approximate modelization error I got from this process. I can use that one. So now what I do is I take my approximate model and I use these values here as the variance to define a distribution that I will use as a proposal distribution and then sample the space. And now I could show you, I don't have so much time, so I could show you the result in great depth. But let me just, I can tell you that the sampling, when you do that, are excellent. You can look them up in our paper about this. But I would like to focus on the speed of sampling here. You can obtain results that converge nicely to the true distribution with a very high speed. Here you have a classical MCMC, which is in this case it's actually the misfit hypothesis. A misfit, so the data, and it's going down and down, and it's not equilibrated. You would expect it to kind of flatten out at some point, but after 2,000 iterations, it has not yet converged to any equilibrium sampling. It's far away, but the method I just proposed, it just jumps, like this, and it just flattens out very quickly. Yeah, and a rough estimation of the difference in convergence time is that the method here I proposed converges between 1,000 and 10,000 times faster than the original one. And I don't have time to say more. I can just mention that we did the same thing on a almost 1 million parameter full waveform acoustic problem. And in that case, let me just jump to that. In that case, we arrived at a convergence here, which is let me see if I can find out. Well, this is actually the likelihood. The likelihood, which means that the good models, they have high value of the likelihood. Down here you have the classical MCMC. It starts at a very poor likelihood, and then it will never come any close to a good solution, which is up here. It just and shows any sign. If you look at the results, it's just completely meaningless. Outputs from it will never convert because in this case you have almost 1 million parameters. But the other process, the method I just proposed, will after a few hundred iterations, it will actually start stemming in a stable way. So I would say the methodology in this case, it is really pressed to the limits. The method, but it seems that if you go away from the ad hoc blind proposal mechanisms that are usually used and jump using a proposal that is guided by approximate physics, then you are able to significantly speed up your sampling time. I'm not saying that you're not removing fundamental problems from MCMC, like getting stuck for a long while in local maximum. So it's not like that. It's just you're doing the same job as a normal, regular, simple MCMC, but you're just doing it significantly faster. And if you have many parameters, you can, in practice, do things that you cannot do with the other one. Yeah, I think I will stop here. Thank you very much for listening.
Thank you, Klaus. And it's now the question time. I would like to invite the students to ask questions first.
anyone dare to do that after this barrage of stuff? Are any of you using Monte Carlo? Okay, yeah. Does it work?
So you were talking about how like even like the number of dimensions for the problem and then how many iterations it would take for it to be accepted like once. So
Yeah.
does like your method like affect that like iteration time?
I could have, that's actually a nice idea you indicate. I could actually have gone back to this horrible example I showed in the beginning and try to show how the positive effect would be from knowing more about it. That would actually be a good idea. I would actually think about doing that for my coming course about this. So that's a very good idea. Yeah. That's actually that. Why didn't I do that? You know, people, they want to see some problems that look like the problems they solve themselves, so you tend to jump into that. But it's a good idea to show this simple stuff. You may also learn your something.
When you make your model,
Yeah.
sort of take like I'm kind of thinking of sort of a unit distance away from the true model.
Yeah.
And then you make another model estimation, which is maybe another unit of distance away.
Yeah.
Oh, well, you know, it's a unit of distance away from your first model.
Mm-hmm.
But I can sort of imagine that when your dimension is really, really big, it's almost surely never going to be back in the same direction as the true model. So I can't really understand how it's how you're able to get sort of a better estimation.
I think I understand your question, but maybe I was not sufficiently clear about that, because when you do when you define a proposal,
Yeah.
there are essentially two ways of doing it. One is the random walk type. You take a step and then you stop there, take a new step. The one I used here in the last one was actually not a walk. It was a proposal that stays the same. No, it's using. It's not a. You can do both. But what I did here was I wanted to keep it very, very simple to test out the thing. So it's the same. The proposal is the same every time. It's always at every step is centered at this approximate model, and it has this. And this also means that it's not symmetrical. When the way it's done there, it's not symmetrical anymore. That's why this Hastings term where you multiply with the ratio of proposal is essential. But it's actually not. But you can actually do this step thing if you just make a proposal that makes steps according to this distribution I defined. Then you can do it, and then it will not get away from. It will keep you inside this snake of a possible or reasonable models. So, but you're right. I was probably not completely clear about it.
So if I understand correctly, your proposal distribution is independent of where you currently are, right?
Yeah, for this example it was.
So if you that's a bit problematic, because if you look at an MCMC algorithm, I mean the one that you showed in the beginning, the random metropolis, if you properly scale the step size to the dimension, you get a linear increase with the difficulty of the problem and in complexity, right? There's theory for that. And if you go for an independent center, that scaling is exponential, which makes those algorithms, I would say, it's almost always unusable. I think what saves you here is that you have, due to your approximate model, you have already identified a lot of the directions that you need correctly, and you make a very small low-dimensional update with these centers. But for going to if that dimension increases, you will exponentially suffer with the construction of this site.
It's true that this you can say that with this proposal I kind of narrow in the space of places where I will look. But and it's true that when you increase the dimension, then that even that space will grow. Definitely.
Yeah, but it would, anyway, we can talk about.
It will grow, but you know, it's something that people sometimes forget. I don't think you forget it, but I think what I see very often is people forget that if you have a space, you're looking for a solution in the space. And let's say it has 1,000 dimensions. Then if you could just narrow in the linear dimension with a factor of 2 for that space, then the gain in the number of points that you're left with is just enormous. It's two to the power of 1,000 smaller than the original ones. Even this that looks not like very much, it's just a huge deal. And I think there's a bit of that. I mean, actually, this is the big part of what is going on here. That you're kind of finding some, maybe not this direct dividing, but you're finding some reasonable model, and then you shrink the distribution around that one, and then you gain, of course, a lot when it's high dimension. But you are completely right, of course, that it doesn't. It will, if I could increase the dimension, then of course that even that smaller space will of course exponentially grow. That's no doubt about that. Of course it will.
I have a slightly different point. I explained.
Okay, yeah, good. Yeah.
Can you maybe clarify what you do, first order model, a second order model?
Yeah, yeah.
What sense do we talk about?
No, yeah. You know, I said that when we were around here, I think. So this is the correct model. This is the first order approximation, which I got by taking this simplified physics and doing the inversions, you guess the way. So my method to find the modelization error. Well, in the ideal world where I knew everything, I could just subtract the 2 and then I had the modelization error. But I can't do that because in the real world you don't have it. So what I do is I say, okay, I will now play a numerical game where I assume this is the true model. And then I can make an approximation from that one. I can do the correct full waveform data from that, and then I can invert that full waveform data from that with the simple method and arrive at an even worse approximation, which I call the second order approximation. And then I could subtract the 2, and then I can find the modelization error. In that case, I can do that because I have that one. I have the new one. And why is that any good? It's any good because this one is, I assume, it's sufficiently close to that one. So the modelization error I get from this game would probably be close to what the true one. That's the idea.
What are the requirements then on the first order model?
Oh, yeah, I didn't like that question. This is the kind of question that I always would ask myself if I was a reviewer. And you're right, it's not mathematically solidly defined. I admit that. It's a very practical thing. The good thing about this is that you follow the rules of this kind of Monte Carlo, so you will, even if you have a very poor approximation, then you will asymptotically sample correctly. Yes, that's a good thing. But
Even if the first order model is complete rubbish.
yeah,
You're not getting worse off. They're not using
that's right. As soon as your proposal spans the entire space, that's of course a requirement. So you will sample it. You're only suffering in time. Only that could
I think you're almost guaranteed to run out of patience.
I guarantee to
run out of patience to wait for it. If your approximation. Right,
yeah. I mean that's true, but you should of course compare to what would happen if you tried to do the plain MCMC on the original one, and that would be completely impossible. So it could remain impossible. So I admit that.
I'm wondering what would happen to the experiment where you kept on making more and more n-order approximate models.
Yeah.
Would it converge to a universally bad model? Would it diverge?
That's an interesting question. I like that question. It's a very mathematical question. Oh yes. Oh my God. I don't know. It's an interesting thing. Where does it go?
Yeah.
It's quite interesting. one could actually do that in America to see what happens. When you just do some it will convert to something simple. Who knows? Interesting. I don't know what the answer is to that. I think it's definitely something that if you cannot make a decent approximation, I mean, it assumes that we can do that. And then, of course, it's not in order to do that. We also need to do the approximation using physics that can make you do a quick preliminary inversion, so you can actually get your approximate model, approximation. In the higher, in this 2D example I just showed, flashed at the end where you have almost 1 million parameters. It was we had a case where we had 2D acoustic data, full waveform, and in that case, making the approximation was done by simulating what they do in, for instance, oil companies when they take the data and do a standard processing of the data, try to generate a rough model and so on. So use that to generate the approximate model. So the idea is that it doesn't even have to be an analytical solution. You can have a procedure that generates a rough model. In that case, the model was reasonable still, but not, of course, some distance away from the true. Yeah, I think this. We wrote 2 papers about this. The first one, which has this one, I think is kind of the most basic, clear one. The other one with the 2D is a much more. It involves a lot of things that may, if you have not read the first one, it may be a little bit may obscure the essence. If you, I think you need to take them in the right order, the order, basically. But that's one thing. That is the. I don't remember which one of the papers you had this. The reviewer was, we had some very good reviews. The reviewer tempted us to, because we claimed at some point that a method that is very popular at the moment is called Hamiltonian Monte Carlo. But that method is a special case of what we do here, because you're using special properties of the data, which inputs information from outside, so to speak, to improve the algorithm sampling. So we were kind of forced to demonstrate that and show that. And so that's actually in the paper, I think it's maybe the second paper where the one with the 2D example. There's actually a chapter about explaining what the Hamiltonian Monte Carlo is adding to the problem in order to make it more efficient. So that's something that was quite a nice challenge, a little bit annoying when we got it, but it was nice and a nice thing. Look at this.
You opened the talk up by showing bimodal distribution. Would your method find the bimodal solution one was appropriate?
If the approximate physics has also leads to a bimodal, maybe a rough bimodal distribution, then it would help. And that's actually one of the basic ideas here, that maybe since we stick to a physics model, even a rough approximate physics, then those approximate models, they will contain more structure than normal proposals. So if that is the case, if there's a bimodal distribution in the approximate physics, it would help you to find it. But having said that, if it doesn't, then you are not better off in that respect than any other method. It may help you still, but we're not claiming that this method is free of many of the problems that an MCMC may face, like entrapment in irrelevant solutions, unless it is the approximate physics captures that part. But the hope is, of course, that if you have a problem where the approximate physics actually captures even solutions that are far away from maybe from even far away from each other, they may actually be able to jump back and forth between separate peaks of the distribution. But I would be very cautious about talking about saying that we can solve all these things. There is some narrowing in. I mean, in this proposal I talked about, it kind of defines a subspace, non-zero in a subspace surrounded by what we call the approximate model, and there is, I mean, so there's some locality in it, and that locality, if it's a too simple definition of the proposal, that locality has the same problem as any other local narrowing in procedures. Only if the normalization errors is sufficiently realistic and the physics is approximate physics good enough, then you may be able to capture this. So it's not. I'm not saying that it's a miracle that will allow you to find solutions in all cases.
Is there a way to tell whether or not the approximate method is good enough or is too approximate to give you what you want, what you need?
I think that I mean, if it's too approximate, so to speak, too bad, then it will take a long time to arrive at equilibrium. And what do I mean by equilibrium? I mean that the outputs, the misfits or the likelihoods of the outputs model, when they are fluctuating around some value that is sufficiently close to the misfit is sufficiently close to zero, and from statistics you can estimate what that means, how close it should be. If you have a prior distribution that is not too demanding, not too narrow, then and you have n data points, then it's n over 2. That is expected value of the likelihood. It's the chi-square criterion. So you can see when you look at the misfits or the likelihoods, you can kind of see that, let's say, if it has properly converged, it will give you values in the right size, but you cannot you cannot guarantee that you could have jumped elsewhere and have the same good likelihoods on this fits. So you can see when it has not properly converged. Let me say that that's the same thing.
But you cannot see what it might be missing.
No, I don't want to oversell it that way. So it's just, this is a speed thing. So if you have a regular MC that is doing a semi-good job, not totally good job, you may be able to produce another semi-good job with this method more fast. That is what I would say. So I don't want to say that it's not. I mean, because we're always facing the fundamental thing that when you're trying to sample a space like this room, you're looking for something. You have only been in points where you have been. There's no way. I mean, if you have not been in that corner over there, then you don't know it's over there. It's still a fundamental problem that we cannot run away from. Except if we know something about it, then if you know something about the shape of the distribution, so it should be small out there for some other reasons, then maybe we can do something. Then we start talking about then we are in the debating about it. So yeah, that's the it's a speed thing. You are on speed for the users.
Okay, limited by the time. We will. Oh, by the way, if there's any question from the online audience. Okay, if there's any further questions, feel free to contact Klaus via email or just going to Peter Gersthoff's office to find out for further discussions. Thank you, and let's thank Klaus for the excellent talk again.
You can take it or leave it.